Welcome to Fourier sine series. So again, let's consider a function f. Defined on the closed interval 0L. And we can create an odd extension of f. By setting f of x is equal to negative f of negative x for negative L less than or equal to x less than 0. Then this is an odd function. So this becomes an odd function. So its Fourier series is a sine series. And once again, we get our f of x is equal to the sum from n equals 1 to infinity, b sub n times sine of n pi over Lx. And our b sub n's are equal to 2 over L times the definite integral from 0 to L, f of x sine of n pi over Lx dx. Again, our integral is just off of the original domain of f. So we integrate over the original domain of f. And we call this series the Fourier sine series. On 0L. So for one function that's defined from 0 to L, we can create both a Fourier cosine series and a Fourier sine series. The Fourier cosine series is assuming that we extend f to be an even function. The Fourier sine series, we assume we extend f to be an odd function, but both are just based off of the same function f defined on 0 to L. So in our example, we are going to work with the exact same function we worked with previously and find its Fourier sine series. So once again, f of x is 1 for 0 less than or x less than or equal to 3. And f of x is 0 for 3 less than x less than or equal to 6. So our Fourier sine series, we have that f of x is equal to the sum from n equals 1 to infinity of b sub n times sine of n pi over 6x. Again, our L is 6. We have our b sub n is equal to 2 over L, so 2 over 6 times the definite integral from 0 to 6 of f of x times sine of n pi over 6x dx. Once again, we can go ahead and split that integral. From 0 to 3, f is just 1. From 3 to 6, f is 0. So we are looking at 1/3 times the definite integral from 0 to 3. of sine n pi over 6x dx plus 1/3 times the definite integral from 3 to 6 of 0 dx. Integrating sine n pi over 6, we have our 1/3 out originally. That becomes times a negative 6 over n pi cosine of n pi over 6x, evaluated at 0 and 3. So we are looking at a negative 2 over n pi times cosine of n pi over 2. And then we are subtracting off a negative 2 over n pi times cosine of 0. Cosine of 0 is just 1. Cosine of n pi over 2 is a little more complicated. So once again, we'll do a little work to get there. But so far we are looking at a negative 2 over n pi times cosine of n pi over 2 plus a 2 over n pi. So note, if we again draw our unit circle, I apologize for my sloppy unit circle. Cosine is 0 for all odd multiples of pi over 2. So these 2 points, cosine is 0. And those are precisely our odd integer multiples of pi over 2. And then our even integer multiples were either 1 or negative 1. So if we're looking at n equal to 4k, that will be the case where we're looking at cosine of 4k pi over 2 boils down to cosine of 2k pi. And this is, of course, our 1. If, on the other hand, we are looking at n equaling 4k plus 2, which are off multiples of 4, but they're still even. In this case, we would be looking at cosine of 4k plus 2 times pi over 2, otherwise known as cosine of 2k plus 1 times pi. And that will give us our negative 1. So we have sort of 3 interesting cases going on. We have the case where we're 0, we have the case where we're 1, we have a case where we're negative 1. So again, our zeros come from n being odd. So what we get is our b sub n is equal to, for n odd, we will just have 0 plus 2 over n pi. For n being a multiple of 4, we have 1. So we wind up getting that we have 1 times negative 2 over n pi plus 2 over n pi. We have negative 2 over n pi plus 2 over n pi. in the case that n is a multiple of 4, so n equals 4k. And then we have negative times negative 1 would be positive, so we would have 2 over n pi plus 2 over n pi. In the case that n is equal to 4k plus 2, I'm actually going to go with 4k minus 2, so we can start at k equals 1. So what we get here then is our b sub n is equal to 2 over n pi if n is odd. That's equal to 0 if n is a multiple of 4. And it's equal to 4 over n pi if n is 4k minus 2. So rewriting this out, we get our f of x is equal to, I'm going to do this as 2 separate sums. We'll have the sum from k equaling 1 to infinity of 2 over 2k minus 1 times pi times sine of 2k minus 1 times pi all over 6 and then times x. That's our odd component. Then we'll have plus the sum from k equals 1 to infinity of 4 over 4k minus 2 times pi times sine of 4k minus 2 times pi over 6 x. Of course, we can simplify that if we wish, but this is essentially what we wind up with for our Fourier sine series. So just watch out. In the case that you have just n pi without the over 2, sine is 0, cosine, we get that negative 1 to the n. But when we have the divided by 2 involved, it gets a little more complicated. And I recommend just drawing out the unit circle each time.